So kinematics, displacement, velocity, time, that was the study of how things move. Free fall, d equals vi t plus a half at squared, vf squared equals vi squared plus 2at, vf equals vi plus at. That was the study of how things move. We're now going to look at dynamics, or if you want the non-physics word, forces. This is the study of of why things move or don't move. Not how they move, but how come, why. We're going to be talking an awful lot about forces, so we're going to start off with defining a force. A force is a push or a pull. Lena, that's a terrible definition. The physicist would cringe at that. They would say, well, on the quantum level, a force is an interaction between two objects when they exchange left. There is a much better quantum physics level definition of what a force is. But for us here, Ashley, at Physics 11, if you're pushing on something, if you're pulling on something, you're applying a force. We'll keep it there, okay? Is force a vector or a scalar? It is very much a vector. We're really going to have to pay attention to directions here. Force is a key concept in physics, and so it has its own special symbol, capital F. And I'll put the vector symbol above it to remind myself that it's a vector, that it has direction. Why not lowercase f? Lowercase f, frequency, already taken. Capital F for force. And what are the units? Force is measured in newtons, named after Sir Isaac Newton. In fact, today's lesson, we're going to be looking at Isaac Newton's 3 laws of motion. I'm going to go on an Isaac Newton rant. And the abbrev for newtons is a capital N. One of the things we're going to be talking about a lot here is the net force. Example 1 says, find the net force on the following diagrams. The net force is what you get when you add up all of the forces acting on an object and replace it with just one single uber force that contains them all. Let me show you what I mean. I'll zoom in a little bit for those of you in the back row. So, number 1, what's the net force? If I'm pushing with 5 newtons to the right and 2 newtons to the right, what's that the same as if I wrote that as a single force? I heard it here. Direction, 7 newtons to the right. So I'm going to write 7 newtons right. Now, compare that with B. What's the net force here, magnitude and direction? Give you a hint, not 7. 3, how can you get a 3? You're right, how can you get a 3 from the 5 and the 2? So we're going to do something similar in this unit that we did back in kinematics. We'll let one way be positive and the other way be negative. And then you can either go 5 plus negative 2, 3, or you can, most of you probably just went 5 minus 2 because most of you are happier minusing rather than plusing a negative. Same diff, though. Direction? Right. Situation C. Ooh. What's the net force acting on it? 0. This is a hugely important situation. If you know the net force on an object is 0, you'll learn later on today, you also know that it can't be accelerating. You know that A is 0, which means either this object is at rest or it's moving in a straight line at a steady speed without speeding up or slowing down or turning. You have it's a very, very powerful piece of information if you know the net force is 0. But the fact that the net force is 0, does that mean there's no forces acting on it? No, in fact, there's 2. They just have to be canceling out. There could be many forces acting on something, and you could still have a net force of 0. It just would happen that they'd all cancel out. What about D? This is Physics 12. In Physics 12, we revisit kinematics, the first big unit that we did, and forces, dynamics, and we do them in 2 dimensions so that you can no longer just let one way be positive and one way be negative. We actually have to do something called vector mathematics. So a few of you have told me you're taking Physics 12 either next year or next semester. That's kind of a teaser or a trailer, preview of coming attractions. Next page over. Newton's laws of motion. I got to pause the video and go on my Sir Isaac Newton rant. So Isaac Newton said, I can explain how everything in the universe moves with 3 laws. I will not make you memorize which law is which. In other words, you will never have a question on a test that says, which of the following is Newton's 3rd law? Which of the following is Newton's 2nd law? But you will need to know what all 3 of them are. In other words, you'll need to be able to recognize them. Oh, that's one of Newton's laws. Okay. Newton's first law, often called the law of inertia. If all the forces are balanced, the fancy phrase for that is the net force is 0, like this picture C here. If all the forces are balanced, an object will either remain at rest, if it was at rest, or move in a straight line at a constant speed. I can combine those, Lena, into one sentence by saying, if an object has a net force of 0, A will be 0. Take that to the bank. Is the object accelerating? No, then the net force is 0. I can tell you that as a law in the universe. Oh, is the net force 0? Then the object can't be accelerating. It's a nice law because it works in both directions as well. If an object is accelerating, and remember, you can accelerate either by changing your speed or your direction, or both, then there must be an unbalanced net force on the object. In other words, the net force cannot be 0. We're going to use Newton's first law when we're analyzing a situation to figure out if there are any missing forces. We'll look at a picture of a force diagram and we'll ask ourselves, is this object accelerating? It is? Well, on the picture, all the forces are balanced, but it's accelerating. I know I must be missing a force from the picture. Or the object isn't accelerating. On the picture, the forces aren't balanced. I know I must be missing a force because they must be balanced because it's not accelerating. Very, very powerful tool. Like you to imagine you're in the passenger seat of a car. Newton's first law says, if the car is moving forward, your body wants to keep going in a straight line at a steady speed. When you make a left turn, what happens? You might think, oh, I get pushed against the door because I'm getting forced outwards. That is exactly the opposite of what's happening. Your body wants to keep going straight. But in order to make you turn, something has to apply an unbalanced force on you. The door is pushing on you. You are not pushing on the door. The door is applying a force to you to get you to go around a corner. Actually, this is a weird concept because you're not used to an inanimate object applying a force on you, but I'm telling you it is. Your body is not applying a force on the door. Your body's trying to keep going straight. That's what Newton's first law of motion says. And in order to get you to change direction, something has to apply an unbalanced force on you. What is it? It's the door. Or if you're in the driver's seat, you actually transmit that force to yourself through the steering wheel. You know, notice you're doing it, but you're doing it. So I wrote down here, imagine you're a passenger in a car and the driver makes a sudden left turn. What sensation do you feel during the left turn? From your own experience, you might recall that you feel as if you're being pushed to the right. That's not what's happening. You're not being pushed to the right at all. The driver steers the car to the left. Your body wants to keep going in a straight line at a steady speed. But the door of the car is moving left with the rest of the car. You feel like you're getting pushed against the door, but in fact, your body's trying to go in a straight line. The door is what's pushing on you. That's what's happening to go around a corner. As a rule, next page, any object tends to continue moving with whatever speed and direction it presently has. This can include zero speed, of course. So if you're at rest, you'll probably tend to remain at rest. When your driver accelerates the car, your body tends to stay where it was, and you feel like you're getting pushed back into your seat. So when the driver steps on the gas, you may have thought, oh, I'm getting pushed backwards. No. Your body wanted to stay at rest. Something had to apply an unbalanced force to accelerate you. What applied the unbalanced force? Your seat pushed against you. But because you're not used, Danica, to thinking as that an inanimate object can push on you, you think, because we're fairly egocentric, oh, I'm pushing back against the seat. No, you're not. Seat's pushing on you. Same, by the way, when you hit the brakes, your body wants to keep going in a straight line at a steady speed. In order to bring you to a stop, something needs to apply an unbalanced force on you. What? The seatbelt? But because you're not used to the seatbelt pushing on you, you think, oh, I must have got thrown forward against my seatbelt. No, that's not what happened. Your body wants to keep going in its current state of motion. And the only way to change that is to apply an unbalanced force. This tendency that all objects with mass have to resist changes in their states of motion is given a special name. We call it inertia. And that's why a nickname for Newton's first law of motion is the law of inertia. Every object in the universe that has mass has this property of inertia. The more mass you have, the more inertia you possess, the harder it is to get the object to accelerate, to speed up, slow down, or turn. You can kind of think of inertia as the measure of the stubbornness of an object or its resistance to change. Let me give you a good example, Nick. You've probably seen either in the movies or on TV a big locomotive rushing along and hitting a car that was parked at rest. Often happens in the movies. You might notice that that big locomotive hardly twitches. Did the car apply an unbalanced force to it? Yes, but that locomotive had so much inertia, so much mass and speed, that it barely felt it. Or even more basic, what has more inertia, a bicycle or a logging truck? Be obvious. Logging truck. Because of that, because it has more inertia, that explains why the logging truck is more difficult to get moving, more difficult to bring to a stop, and more difficult to turn on a corner. Now, how do we measure inertia? I'm going to tell you that inertia and mass in kilograms are the same thing. That isn't true because, as you learned in the last unit, as you go near the speed of light, your mass increases. Actually, your inertia is increasing. But I said to you, we're going to pretend that we're never traveling near the speed of light in this unit, so we're going to ignore all the weird Einstein stuff in this unit. You want to know how much inertia an object has? Measure its mass. More mass, more inertia. Less mass, less inertia. Paperclip, lots of inertia or not much inertia. That means you can accelerate a paperclip, hey, just by flicking it with your finger. Okay? Semi-truck, can you accelerate it by flicking it with your finger? No, more inertia. Inertia, mass, resists a force. You can think of mass as a measure of the stubbornness of an object. I said that already. The more mass an object has, the less willing it is to change its motion state. This is what explains why our bodies are backwards accelerometers. I told you last or 2 units ago that our bodies can feel acceleration, but I told you, Zach, it's always backwards. The reason is actually your bodies don't detect acceleration. They detect your inertia, your resistance to the force, which will always be in the opposite direction of the force. I wrote down here car accident story. In 1997, I was a student teacher here, way back when, and I was on my way to SFU on the freeway, and I got rear-ended by a semi-truck. Yeah, it hurt. We weren't at full speed. It was rush hour. We were in stop and go traffic. We were doing about probably 45 kilometers an hour, maybe 50 kilometers per hour. And 2 cars in front of me, someone slammed on the brakes. So 1 car in front of me, someone really slammed on the brakes, really. So I had to do a really quick stop. And the semi-truck behind me, he had just looked down to pick up his cup of coffee mug. And by the time he looked up, bam, he had plowed into me. It hurt. I was driving a 1982 Honda, and at that time, the ashtray, most people who used their ashtrays who didn't smoke, they used their ashtray to store change, because back then, pennies were still a thing. And pennies, you threw them somewhere in your car. You didn't want to be carrying them around all the time. So most people had an ashtray full of pennies. When I got rear-ended by that semi-truck, my ashtray full of pennies shot over my shoulder and hit the back seat. No, that's not what happened. Actually, what happened is my car got thrown forwards, and that tray of pennies had enough inertia, enough mass, that it stayed where it was. But because I got thrown forwards, it appeared to me like it had gone zipping over my shoulder and hit the back seat. Actually, no, it stayed where it was. Me and the car got thrown forwards. It was a really nice physics example. Aside from the whole car accident thing, there was some really nice physics going on there. Magicians do a similar thing when they yank a tablecloth out from underneath dishes. I have my own version of this. Here's a nice one. Put your pencils down, look up. So, shopping carts, see them? Do they have mass? Yes, they have a fair bit of inertia. What's their speed right now? What's their speed right now exactly as a number? They want to maintain that state of motion. They really want to maintain that state of motion. Jan is looking at something else instead of the video. I don't know why you'd be doing that. Look up and watch. Okay? That's not my favorite part. Watch this guy here on the right. Wait for it. Wait for it. That look right there, you're near the front. Can you read the timestamp?
7:57.
I'll bet you his coffee break starts at 8 a.m. Look at his face. That's a person going, I wonder if I can start my coffee break 3 minutes early, because I do not want to be around to clean this up. Come on. That's what I'm seeing on that face right there, right? That's someone doing a little bit of math, looking at the clock that's on the back wall. Coffee time? I think so. Another one here. The subway is traveling to your left. So this person is moving to the left. What happened? Okay. Newton's first kicked in. His head wanted to keep going in a straight line at a steady speed. Now, his body didn't move because the bench was able to apply a force through his pants to his body. The bench was able to bring him to a stop with friction. But there was no force attached to his head. His head kept going in a straight line at a steady speed. Remember that. We're going to come back to that one in a few minutes. This is a really neat one, one of my favorites.
Here we are at the International Space Station. We're doing a reboost right now, and we're showing that the space station is actually accelerating away from us.
So this is the space station. The space station actually isn't completely out of Earth's atmosphere. It's almost out. Like the atmosphere there is really thin. But it is scraping along a tiny bit of Earth's atmosphere. And so every few months, Jan, they have to boost it back up a little bit. Right now, they've just turned their boosters on. The engines are causing the space station to accelerate out of the page towards us. And here's what's neat. When the astronauts lift their feet up because they're at rest relative to the space station, we're going to see the space station accelerate away from them, and they're going to stay in one place. Now, to us, it's going to look like they're moving backwards. They're not. We, the camera, are moving away from them.
We're going to float in the middle of the cabin, and it started already. We start off, stop, turn on the camera.
By the way, under Nerd Trivia, How come their faces look so red? Well, their heart's always been pumping against gravity and it hasn't adjusted. Yeah, if you ever see the astronauts, they'll tell you your face always feels a little bit red and you always feel like you have a stuffed nose because turns out gravity is also what clears your sinuses out. So you just always feel like you have a stuffed nose. Food tastes kind of, you know how food tastes weird when you got a cold? Everything tastes like that up there as well. Just a little nerd trivia for you.
And we get moved, the space station's accelerating, leaving us behind.
And they are speeding up. They are accelerating. It's not a constant speed because we are accelerating away from them.
Ooh.
That's amazing. I'll do it again.
This astronaut is one of my favorites. He was on the space station about 10 years ago. He's from Japan. If you take Physics 12, you'll see another video of him on the space station. He did something in his free time that if any of us had thought of it, of course we would have so done that in zero gravity on the space station. I won't tell you what it is. That's also a teaser, a little trailer, a little preview of coming attractions.
Okay. Floating still.
Oh. Wow. Wow.
These all have engineering degrees and PhDs, but I'm telling you right now, they're 8 years old, and all they got is, wow, whoa, because this is just pretty cool. Okay?
Oh. Oh.
So, Newton's first law, the law of inertia. If forces are balanced, then A must be zero. If forces are not balanced, A can't be zero. I also had one more, but I can't find those. Somebody didn't put them back on the shelf. So if you're wondering why inertia beads is crossed out, I looked for them this morning, couldn't find them. Next page, here's the short version. If an object is accelerating, there must be an unbalanced force. And it works backwards as well. If there's an unbalanced force, the object must be accelerating. Remember though, accelerating, Nick, can mean changing speed or changing direction. So if you're going around a corner at a constant speed, your direction is changing. There must be an unbalanced force acting on you. About 15 years ago, Chris Angel had a popular show on TV called Mind Freak, and I saw him do a stunt where he claimed that he could be stronger than 10 individuals. And I went, no, that's just good physics. So we're going to recreate that here. Let me pause the video for a second. How does Newton's first law help explain how seatbelts save lives? Let's start applying this already. How does Newton's first law help explain how seatbelts save lives? What if there was no seatbelt and you hit the brakes really fast? What'll happen? You die. More specific. Zach. Can we let's talk about it in physics. In physics terms, your body is going to keep going in a straight line at a steady speed. That's what Newton's first says. If there's no force acting on you, okay. What do you yell when you want the front seat?
Shotgun.
Why shotgun? That's a stupid thing to yell. Why shotgun? I mean, you all yell it. Have you never asked why? Yeah. It comes from two different situations. The more ancient situation from stagecoach days, the driver used to sit on the left on the roof of the stagecoach holding the reins. And then next to him, if they were carrying money, was the guy carrying the shotgun. That was called the shotgun seat to make sure they weren't going to get robbed. But in the 1950s and 60s, especially in the US where they still don't have seatbelt laws, but in Canada we didn't have seatbelt laws at that time, the joke that you used to make was if you were in the front passenger seat, you were sitting in the shotgun seat because in a head-on collision, you'd be the first one out to inspect the damage. You'd go through the windshield, and on your way past the hood, you'd make sure the hood was okay, and then you'd crash. It was our joke. Shotgun, I'll be the first one out to inspect the damage, was our running joke. You were literally in the shotgun and going to get fired out like a barrel bullet. Okay, so how does Newton's first law help explain how seatbelts save lives? I think we can say this. Seatbelt applies an unbalanced force to stop us. Very simple device. Has saved thousands and thousands and thousands of lives, and yet, of course, there are still some states. You can't make me wear a seatbelt. It's amazing how many professional athletes don't wear seatbelts, especially in basketball. I have seen far too many NBA players who get into a car accident and then you read, and their body got thrown from the vehicle. How can your body get thrown from the vehicle? The only way is if you're not wearing what? Seatbelt. And so I know of at least 3 or 4 basketball players whose careers were over. They survived, but their careers were over. I have no sympathy. You were worth millions of dollars. How about as an insurance, you maybe clip your seatbelt on to make sure you don't get injured in a car accident? Why wouldn't you want a seatbelt on a motorcycle? Read what? Okay, because the motorcycle wreckage can tumble. We don't want you attached to that. If the car tumbles, you're inside a roll cage. You're inside a pretty safe area. Safest place to be in a car accident is inside the car. But yeah, I don't want to be attached to tumbling wreckage. And because the motorcycle has a different mass than you'll decelerate at different rates. You'll just naturally tend to separate, which is probably good. Yeah. What about convertibles? Those typically are, first of all, they're more dangerous. Okay? Yeah, if you're riding a convertible, you're more dangerous if the convertible rolls over. Typically, a convertible is usually, though, a sports car. Usually, they're lower and wider, so they're harder to tip over in the first place. Like an SUV can roll much easier than a convertible. And there's a good chance that if you flipped over, depending on what the impact is, you would just naturally be forced into this position, so you'd be okay. But yeah, there's still a risk there. So what do we want to say here? We don't want to be strapped to tumbling wreckage. Okay, why don't they have seatbelts in school buses? But wouldn't that save lives? Probably, but none of you pay taxes, so they don't care. Sorry, truth hurts, but your parents will complain, but that's about it. Also, sorry, I should say, because a bus has a large mass, a large inertia, in an accident, it's not going to slow down or decelerate as fast as a tiny car. You may have heard the commercials that were on a few years ago that said speed kills. Speed does not kill. Acceleration is what does the damage. We'll talk about car accidents in more detail later on in this course, but as a starter, you want to know what does damage? It's acceleration. If you can reduce acceleration, less damage. And because the buses have so much inertia, they're not going to decelerate as fast for the same force. Yes, if they hit a brick wall or something, but in a head-on collision, they're not going to decelerate as fast. Let's do some numbers here. It says this, Manuel weighs 1,000 newtons. What that means is gravity is pulling down with a force of 1,000 newtons on Manuel. And he stands on a board that weighs 200 newtons. Gravity is pulling down with 200 newtons. The ends of the boards rest on bathroom scales, and it looks like from the picture the bathroom scales are pushing up. They have to be pushing up. Here's how I know. Look at this. Is Manuel and the board sinking into the ground like quicksand? Be obvious. Are they sinking into the ground like quicksand? Everybody? No. Are they flying into the air like Superman? Everybody? You know what that means? That means the forces must be, I'm looking for a word that starts with letter B. The vertical forces are balanced. Lena, what's the total force down? Please do the math in your head. What's the total newtons down? What must the total newtons up be? Same number. You're right. No. Yep, 1,200. Okay, what must the total newtons up be? Same number. How do I know? Because if they weren't imbalanced, he would have to be either sinking into the ground like quicksand if the downwards one was bigger, or flying into you like Superman if the upwards one was bigger. Is he? Say no. So the forces must be, I'm looking for a word that starts with letter B, balanced. Okay, so how many newtons is each of these scales pushing up with? Best guess. 600 apiece. How do I know 600 apiece? Because we're dead center between the two of them. Now, in the next one, Manuel's going to move to the left a little bit. Again, Zach, what's my total force down in this next picture? Is he sinking into the ground like quicksand? Is he flying through like Superman? That means vertically the forces must be, I'm looking for a word that starts with letter B. The left-hand scale is pushing up with 850 newtons because he's closer to it. What must the right-hand scale be pushing up with? Has to be. Has to be. Let's do a little bridge engineering. A 12-ton truck is 1/4 of the way across a bridge that weighs 20 tons. A 13-ton support is pushing up with 13 tons of force. Is this bridge sinking into the ground like quicksand? I hope not. Is this bridge flying into there like Superman? I hope not. Danica, what's the total force down? What must the total force up be? Same answer. Well, if I got 13 tons over on the right, what's this other support pushing with? Has to be. Has to be. If not, then that bridge could not be not accelerating. Could not be at rest. Example 3, in terms of Newton's first law, the law of inertia, how does a car headrest help to guard against whiplash in a rear-end collision? And your hint is, remember the subway sleeper. Okay, so if you get rear-ended, what applies a force to your body? The seat. Is your head touching the seat? No. So your body is going to get accelerated forward, but much like the subway sleeper, your head is going to stay as it was, not moving this time. It's going to want to stay at rest. And that's where you feel like your head got yanked backwards. Actually, your body got forced forwards. What's the simple workaround? Put your headrest there. And my advice to all of you, once you get your first car, first thing, please, people, take 20 seconds, adjust your headrest. It's such a simple fix and almost no one does it. You can save yourself a lifetime of injury by that little 20-second fix. So I don't want to write a big paragraph. I would say something like this. Applies unbalanced force to accelerate head forward. Okay. Again, it's not speed that does damage, it's acceleration that does damage. If it was speed that does damage, none of those Formula One racers would ever survive a car crash. But they've gotten pretty good at minimizing the acceleration as best they can. So that's Newton's first law, the law of inertia. If you're accelerating, forces can't be balanced. If you're not accelerating, forces must be balanced. The net force must be zero. Newton's second law is the equation. It's really the only equation you're going to get in this whole unit, but from it, we're going to derive a bajillion equations. Newton's second law tells us how to calculate force. It's F equals ma, where F is a vector and A is a vector. In fact, force gets its direction from the acceleration. If you're accelerating north, the net force is north. If you're accelerating down, you know which direction the net force is? Down. Okay. Is this on your green sheet? Find it. Okay. That row has 3 equations. Those are the only 3 for this whole unit. You don't have to memorize this one. You should. I've done you a huge fave if you memorize it. In fact, I'm going to say to you, F equals what? And you're going to say MA. F equals what? F equals what? F equals what? I'm going to keep going until it's obvious that every one of you is saying it out loud, because right now it's painfully obvious that most of you aren't. F equals what? F equals what? Worth memorizing. Oh, how many variables does that equation have? It's actually 3 equations in one. Surprise! By the way, this also means that 1 Newton, force is measured in newtons. It also means, well, what's mass measured in? What's acceleration measured in? Technically, a Newton is a kilogram meter per second squared. In fact, that's what we wrote for a long time, but about, I think, 70 years ago, there's an international committee that names units. They decided to name the kilogram meters per second squared the Newton after Sir Isaac Newton. F equals what? MA. Example 4. Malcolm, actually, do me a favor. Cross out the word Malcolm. Put the word Nick there, please. Nick has a mass of 65 kilograms. What's the magnitude of the gravitational force acting on him? Ooh. Huh. Ashley, what's this asking me to find? Force. F equals what? Let's write that down. Ashley, did they tell us Nick's mass? Did they tell us Nick's mass? Yep. Hey, ooh, Ashley, what is the acceleration due to gravity? You know this, all of you know this. We're not going to include the negative because I said magnitude, but 9.8. If Nick did have a mass of 65 kilograms, I don't know what your mass is, this is how strong gravity is pulling him to the earth in newtons. I can do this in my head. Give me 650, take away 637, double check me. Yeah, units, Ashley, it's a force. What do I measure force in? No, we have a much shorter way to write that. Yes, if you write kilogram meters per second squared, I'll give you credit. But what's the shorter way to write that, everybody? Newtons. Okay. This is important, and I'm going to be fussy on it. In fact, I'm going to do a whole lesson on it later on, but I'm going to start right now. Gravitational force has a special name, a synonym for gravitational force, for the force that's pulling you down to the earth, is weight. Weight is not measured in kilograms. If you tell me an object has a weight in kilograms, I'll take marks off. Weight is measured in newtons. Mass is measured in kilograms, and they are not the same thing. Your mass is the same anywhere in the universe, but your weight depends on what planet you're on. If you're on the moon, you would go not 65 times 9.8, it would be 65 times 1.6. That would be your weight on the moon. It changes. If you're on Mars, it would be 65 times whatever the acceleration due to gravity on Mars is, about 3.3. So your mass, kilograms, that's the same anywhere, even near a black hole. Your weight is very much location dependent. Cross out Malcolm again. Nick stands. Nick, could you please stand on your lab table, please? Nick stands on a table. Stand up. Come on, you've always kind of wanted to do this. Get up. Stand in the middle, please. Okay? Glare down upon us from on high. Take a look at Nick. What are the forces acting on him? Gravity is pulling him down to the earth, yes? Is he accelerating into the table like quicksand? Is he flying off of the table like Superman? Then there has to be another force pointing up, canceling out gravity. So part 1 asks, what is the magnitude of the upward support force, stay there, that the table exerts on Malcolm? I can tell you exactly how big it is to 3 sig figs. Is he sinking into the ground like quicksand? Is he flying here like Superman? Then how hard must the table be pushing up? No. That's an acceleration, not a force. Bad guess. What? Darn right it's got to be pushing up with 637 newtons, because if the forces weren't balanced, Nick would either be flying into the air like Superman or sinking into the table like quicksand. Is he? Then the net force on him must be 0, and the only way that can work is if there's an upwards force of exactly 637 newtons. How do we know that this force exists? Newton's first. Newton's first law of motion. Are you sinking into the ground like quicksand, Nick? Are you flying here like Superman? But I'm telling, and this is a weird one for us to realize. The table is pushing up on you. It must be. And for an inanimate object to be applying a force sounds weird. Trust me, they do that all the time. Otherwise, our universe would not work very well. Thanks, Nick. You can climb back down. Unless you want to stay up there. If you want to stay up there for the rest of the lesson, you have my permission. You could. It's kind of neat to glare down on people. I wrote here, hint, represent Nick with a dot and draw the forces. Here's a really, really handy toolkit piece that I'm going to give you in the same way as 2 units ago I gave you DFIC, list your data, find a formula. If you want me to give you the same very, very handy tool, it's something called a free body diagram. We're going to do a whole lesson on it, but I'd like you to draw a little dot. That's Nick. Everybody, draw a little dot. Okay? What are the forces acting on Nick? Get the obvious one. It starts with letter G. Draw an arrow pointing down, and we're going to label that with 637 newtons. If that was all there was, which way would Nick have to be accelerating if that was the only force? Have to be accelerating down. Was he? So I'm going to draw an arrow pointing up. How long? Eyeball it. Make it the same length as your arrow pointing down. So I'm going to eyeball it. This is F table, and I know that that has to be exactly 637 newtons. We're going to use this representing the mass with a dot and putting the forces with arrows trick all the time. This will be the single most useful tool that I give you in this unit. We're going to do a whole lesson on it. But for what it's worth, we call a diagram like this a free body diagram. Although, Emma, it's no surprise because I tend to abbreviate. After I teach you that, I'm going to abbreviate it with FBD in my notes for the rest of the unit. Free body diagram. But you're often going to hear me say something like, what is this a good job for? And you're going to say, oh, free body diagram. Turn the page. Let's do some numbers. The space shuttle has a mass of 2.03 times 10 to the 6th kilograms. If each engine can exert a force of 12.5 meganewtons, what is the maximum acceleration of the space shuttle? Note, there are 2 engines. Okay. Huh. Ooh. Lena, what's A asking me to find? No, I picked on you already. Nick, what's A asking me to find? So, Nick, let's do our old reliable. A equals question mark. You okay with that? Nick, do you see a VI or a VF or a D or a T anywhere in this question? No. Okay, so I'm not going to use those 4. In fact, what's kilograms measuring? Do we have an equation that has mass and acceleration in it? F equals what? Ah! Although, Nick, what did you say they want us to find? How would I move the M over? How will I get the A by itself? What's that? Say it. You're right. Say it again. We have a new equation. You know what, Nick? We're going to name this after you. We're going to call this Nick's theorem. Okay? If I want to find A, I can find A using Nick's theorem if I know the force and the mass. What's the force? Well, first of all, how many engines? 2. And then 12.5 mega. Can someone on the green sheet, what's mega? 10 to the what? 10 to the 6th? I can just go times 10 to the 6th. I don't need to do the full conversion. Divided by 2.03 times 10 to the 6th. Oh, this is good chance for you to remember where your scientific notation button is. Get your calculators out, all of you. Try this on your calculator. Oh, Zach's finally opening up his calculator. Good. Although we really haven't done anything that you needed the calculator for. Maybe the 65 times 9.8, but I did that in my head, so I'm sure you could have. Is this a fraction? You might want brackets around the top, or use your fancy schmancy button. What do you get? I'm doing some rough math in my head. I think you get something around 11, 12-ish. Okay? Because that's roughly 24 divided by 2-ish. Nick, what'd you get? 12.3. 12.3? Is that rounded off properly? Okay. By the way, a lot of you lost silly marks for chopping off, not rounding off on the special relativity test. A lot of you lost a half mark on questions for doing that. 12.3, Nick, units, it's an acceleration. I know, we're dredging stuff up. Good. How many G's is that? How would I figure out how many G's that is? How many G's is that? Could you divide by 9.8? Sorry, how many? What is it? 1.2. Wait a minute. I heard that astronauts pull like 5 or 6 or 7 Gs. I looked these numbers up. These are from the Space Shuttle specs. Have they been lying to us? Do astronauts not pull 5 or 6 Gs? B, turns out, why does the acceleration change as the engines burn? The maximum acceleration is actually just before they shut the engines off, not while they're on Earth. Why? I'm gonna wait, because somebody had the aha moment in my Block B class, so I want to see if one of you will as well. Pardon me? Nope, atmosphere doesn't play big a role. Yeah. Got to be fussy. You're not losing weight. Use a different word that starts with letter M, please. Oh, Nick, what was your theorem? A equals F over M. If we keep the force going, keep the engines at full throttle, how would the space shuttle be losing mass? As they're burning the fuel, their mass goes down. Okay, where is this M in Nick's theorem, on the top or on the bottom? As you divide by a smaller and smaller number, what happens to your answer? Gets bigger. In fact, the acceleration just before cutoff is so big, they actually have to throttle the engines down, otherwise the astronauts would black out. That explains, you may have watched on TV a space shuttle launch or a SpaceX launch, or whatever, and you may have noticed they leave the ground pretty slowly. It doesn't look like they're pulling that many Gs at all. No, they're pulling their maximum Gs up there somewhere, because as M gets smaller, A gets bigger. Is that all right? I don't want to write a big paragraph, but I want to, how about this? We'll write Nick's theorem as M decreases. My abbreviation for decreases is an arrow pointing down. What would be a good abbreviation for increases? An arrow pointing left. Oh, up! That's way better than my left. Yeah, I like that. That was a joke. Oh. How does Newton's second law help explain why a sprinter might want to wear lightweight shoes? I have no idea what you said. How? I think this is a job for Nick's theorem. Let's write down A equals F over M. So let's suppose you're an Olympic sprinter. You've lifted weights, you've worked out, you've lifted weights, you've worked out, you've maximized your strength, you've made your force as big as possible. How else can you control your acceleration? Lighter shoes, bigger acceleration. Yes? In fact, it's going to be the same thing. As M decreases, A increases. I'm a little amazed that no one has invented the following product. To me, the best way to do, especially the 100-meter sprint, no shoes at all. Instead, have a liquid polymer that you roll onto their feet. Then you have a tread mold that you stamp while it's still liquid. That gives them the tread. And you could have different tread molds for different track conditions. And it lasts long enough for one race, and then you just peel it off. Because the laces and all the fabric on top of their feet, that's wasted mass. And you've watched the Olympics enough to know what the difference between first and eighth is, a few hundredths of a second. So you're talking, small changes will make a huge difference. If any of you go into materials science and you decide to market the device that I've just mentioned, feel free to give me 10%. But I'm thinking if you could come up with something like that, it would sell to the Olympic level athletes. Because top half of the shoe is wasted mass. Totally. We're going to pause here. Tomorrow, we'll look at Newton's third law. Newton's third law is the one that explains that everything that you thought works one way works backwards. But before you put stuff away, if you want to get a head start, you are capable of doing this first part 1 Newton's laws homework. So if you want to turn to this right now, I'll just let you look at it and I'll walk through this. It says this. So find the little picture of the little girl hanging from the swings. It says Nellie Newton wants to be a gymnast, and she hangs from a variety of positions as shown. Because she's not accelerating, Zach, who's not on his phone right now, if she's not accelerating, the forces must be, I'm looking for where that starts with the letter B, balanced. It says she weighs 300 newtons. In other words, gravity is pulling down with 300 newtons. In part A, how hard must the scale be pulling up with then? Exactly. Folks, we're not done. Have a seat. I'm going over the homework. Shouldn't be packing up your book yet either. If Nellie is being pulled down with 300 newtons, how hard must the rope be pulling up with? What about here? If we're splitting it between 2 ropes. Okay, see if you can figure out the rest of those. I put the answers down here. So you can try those tonight as a head start if you wish. Now you can shuffle and put your books away. Oh,